Hi everybody, welcome to another IZ8 DWF arcade repair video. I've got a Cascade PCB made in Italy by Sidam. This is a clone of the arcade game Avalanche, released by Atari in 1978. And here we have my favorite 8-bit CPU, the glorious 6502. Together with the PCB, I've also got all the control harness. As it often happens on these old PCBs, I spotted some missing ceramic bypass capacitors. And here there was another one. Some others are still present but broken. Of course, all of them have been replaced with spare ones. Then, as always, I'm checking all diode and transistor junctions. This diode shows a too high forward drop, however. It shows more than 1.8 volts, and that can't be good. The diode is only marked with 1T, as all the other diodes on this PCB. However, the other diodes showed the usual 0.6 volt drop, so this one was substituted with a 1N4148. Now, this board is so far the one that required the most complicated connection setup, thanks to some peculiar design choices that were made by the Atari engineers. First of all, it needs a few different supply voltages. Here I connected two 13-volt transformers to obtain what in this picture has been labeled as 25 volts AC. In practice, they mean 25 volts total with a center tap. Since I didn't have a center tapped transformer of the right voltage, I ended using two of them connected with opposite secondary phases. This supply is rectified and regulated on the game PCB to obtain plus 12 volts and minus 5 volts for the dynamic RAMs and the 2708 EEPROMs. One positive rail is also used by the audio amplifier IC. Then we have the 10 volts DC. This is regulated down to 5 volts by an onboard linear regulator for all the TTL logic chips. I've used a 9 volt 3 ampere switching supply for this one. I needed also yet another transformer to obtain about 5 to 6 volts AC for the incandescent lamps on the start buttons. In this case, we really need an AC voltage for the lamps, since they are turned on by triacs, and these devices can turn off only if the current passing through them goes to zero, which is something every AC current does 50 or 60 times per second. And by the way, this part of the schematics is wrong, as the plus 5 volts are for the serve LED, not for the credit lamps. Then I've connected two switches for the coin inputs, and I really needed proper switches because they used the normal closed contacts for the rest position. If I'd leave one coin connection open, it would get coined continuously. Also, all the start and serve buttons need to be normally closed, so I've wired individual connectors to the appropriate pins of the control harness to connect all of them. This includes also the serve LED and its dedicated 5 volts DC wire. Even the test switch needs to be normally closed to ground, so here is another little switch hiding under the wires. The paddle control is obtained with a potentiometer that needs 3 additional wires to be soldered. Then we need to connect a speaker for the sound effects, but the volume potentiometer is external and I didn't get it together with all the wirings, so I've just got a power resistor with different taps and I'll select the one that gives a suitable audio level. And of course, if you look carefully, you can spot a video cable that goes to the monitor. Luckily, this is a black and white game. So let's power on. Well, it seems the attract mode is running, but the video circuitry has problems for sure. Even switching to the self-test diagnostics doesn't give much help apparently. According to the Atari manual, the test should display some messages if it finds bad ROMs or RAM ICs, but all we got is some partial words on the screen. However, there is another information here. Buttons will only illuminate if the RAM and ROM tests found no errors. So let's flip the test switch. And yes, all lit up. So it's time to understand how the video circuitry works on this game. First of all, let's have a look at the memory mapping. Here we see that the total RAM area is 8 kilobytes wide, and that almost all is display area. Only the first two pages from 0 to 1FF, or in other words, the first half kilobyte, is not used as video RAM, and that makes sense since page 0 and 1 are special for the 6502, since page 0 is the fast access RAM segment and page 1 is the stack area. Now, the whole RAM area is made with 16 dynamic RAM ICs, and each of them is 4096 by 1 bit wide. We can also see that the address multiplexers allow either the CPU to access the RAM during its active clock phase, or the video vertical and horizontal address counters to scan the memory area during the inactive CPU clock phase. This also means that there are no separate counters for refreshing the RAM, since all the raw addresses are always generated by the video scan counters for every frame. Now we are pretty sure that at least the page 0 and stack areas are working and addressed correctly, otherwise we'll likely observe random crashes and watchdog resets happening. The video output is generated by a parallel to serial converter directly from the RAM data bits. There is no character ROM or anything else in the middle. The parallel to serial shift register is not aware about the screen address position, so since some parts of the output are correct, we can assume the problem is not here. So a possible problem might be in the incorrect generation of the horizontal and vertical address bits. These are made, as usual, with a chain of counters. The Atari board uses the 9316 TTL counters, but on this clone I've found a chain of 74 LS161 that are almost identical. I haven't found any bad output on all the divider chain, and I think that is working fine also because some sync signals are generated by this TTL prom plus the LS175 register IC. And if we had problems on the counter chain, then probably also the video sync would not be correct or stable. So, since almost everything else must be working, the only parts that could be faulty are the two address multiplexers that generate the RAM address during the video output clock phase. Of course, I want to find bad signals on these ICs before pulling one or both of them. Now, in reality, before looking at the multiplexer signals, I've tried using this dynamic RAM comparator that I made some years ago, mainly as help in troubleshooting RAM issues on Commodore PET computers. I've added support for the 4027 type of dynamic RAMs now. However, it showed possible errors on too many ICs, so this not only is too suspicious, but it is precisely what happens in case the refresh circuits are not working properly, as is the case if the video address multiplexers are faulty in this PCB. So I started checking all outputs. A good output looks like this. I'm triggering on the enabled signal going low, and that's the upper scope trace. On the lower trace there is one of the multiplexer outputs. The only relevant part of it is during the low enable period. We can see both the high and low levels displayed in successive sweeps. In real life, there is also a visible transition roughly in the middle of the enable period, that is, the address transition from row to column. This is another good output where the address transition got somehow in sync with the camera frame rate and is clearly visible in the following short video. However, some outputs are indeed looking bad. Here's the first one. This is always low. And also this one is bad. For sure, in the raw address phase, there's never a low output, and also the high levels appear split into slightly different voltages, so with two bad outputs, this IC is clearly faulty. So the faulty 74LS257 has been substituted with a spare one. And yes, now the video output looks fine. Dip switches are set for Italian language, it seems. Even the test mode looks good, and rotating the pedal potentiometer has the right effect on the number displayed in the third row. Then I tried flipping the dip switches because I wanted to obtain one coin for one play. I tried switching them all and I could obtain all the supported languages. But it seems one of the coin option switches is not working. The only other option I could get is 2 coins per play. According to the Atari manual, coin options are selected by switches number 3 and 4. However, by simple PCB inspection, I could observe that on this clone, switch 3 is unused and instead switch 5 is connected in its place. The 2 credit switches are read through a bus transceiver enabled by the IN0 signal. And this signal is generated by a chain of 2 decoders, and I could easily verify with the logic probe that it's toggling correctly. By the way, they didn't use the 8T97 IC on this PCB, but another very unusual one, the 81LS95. But luckily, there is a 74LS IC that's pin compatible with the 81LS part. However, let's first try to see what's wrong with it. The CPU reads the switch position by accessing the 2000 hexadecimal address. However, the game code only reads that location during the vertical blank interval, in other words, 60 times per second. It is very difficult to capture such a short and frequent interval with my analog scope. However, there is a simple workaround. I can install an op generator socket under the 6502. With this socket, the CPU will cycle continuously over the whole address space. In this way, I can easily see any single byte access with the scope. As always, the upper trace is the select signal. We want to see what happens when it is low. First, I check the buffer input directly connected to the switch. The trace can be either always low or always high, depending on the switch position. Now we check the output. When the switch is grounded, we have a low output during the select interval, and the data bus line starts to drift high when the buffer is not selected. And if we toggle the switch, the output goes high during the select intervals. So far so good. Now we check the other input pin. As always, the trace follows the switch position. So let's check its output now. And yes, it appears to be stuck high. We see no changes when flipping the switch. So this IC is indeed bad. I've then ordered a few 74LS465 that are pin compatible with the old 81LS95 and substituted the faulty one. Now all the coin options work. Let's attempt to play some games. Well, it's a bit difficult because I'm just turning the potentiometer shaft without a knob. Anyway, the game looks and sounds fine. It's all for this video. I hope it was interesting and that you learned something. If you have any question, please use the comment section below. Have a nice time and thank you for watching.